Okay, so I got two curves here. Today is the 16th. One of those curves represents exponential growth. Which one? Blue or red? Ski slope. Yeah, the blue one. This is our exponential growth. One of these represents what we call logistic growth. Growth rates, so that's obviously the red one. This is the S curve. This one's the J curve. So the growth rate is represented by what part of that line? Think mathematically. The slope. The slope of the line. Do the slopes of those two lines start out pretty similar? Yeah. For this whole section down here, the slopes are almost indistinguishable. That starts to change when we get up here, and suddenly the red line, the slope starts to decrease. And then we get some places here where it actually has a negative slope. Population's actually shrinking. Okay, so thinking back to what we had started to talk about, what makes the growth rate change in S-curve growth? What happens? Okay, you could run out of food. What else could happen? What else? Could what? It reaches carrying capacity, but what forces it? What creates a carrying capacity? Okay, so there's got to be some resource that's in short supply. So for the rats, in a normal average year when the bamboo is not producing fruit, what limits their population? Food. How many calories they can get. Think back to our tolerance curves in the last chapter. And in a normal, that middle area, that green area, is where you're getting enough calories to grow yourself and to reproduce. Your population can grow. During a normal year, they have to keep the number of rats down to where everybody gets enough calories to reproduce. You reproduce too much, somebody starts to die. I mean, they said when times get hard, they eat their babies. Ugh. But during the bamboo flowering and fruiting, suddenly that restriction is lifted. Woohoo! And it is a rat reproduction party. Things that limit the growth of a population are limiting factors. Yeah. Remember, ecologists are not all that creative. Limiting factors. So let's talk a little bit about limiting factors as it relates to the movie. So these are from your notes. There are two general kinds of limiting factors. There are density-independent factors. And with density-independent factors, it doesn't matter if there are a lot of you or not. It just kills things off. Like a forest fire sweeping through an area that literally burns up rats. That would be density-independent. It doesn't matter how many there are. It's going to kill whatever's there. A flood that just drowns a lot of rats in their burrows. That would be something that would be density-independent. Density-dependent factors are related to how many, rats per square foot or rats per square acre you've got. And the higher the population, the more densely packed they are, the more of a problem these are. So, lack of food, lack of nesting sites. Disease can be density-dependent. Because if you've got high density, what's true of disease? Contagious disease, anyway. Spreads more easily. During the Black Plague in Europe, some people would flee the cities, thinking they could save themselves by going to the country. Because fewer people, and they didn't really even understand contagion at that point, but it had been noticed that little isolated farm families didn't die in the same numbers that people in the cities did. Unfortunately, those people fleeing the cities usually took their disease organisms with them. So density-independent factors, doesn't matter how closely packed you are, y'all die. Where with density-dependent factors, if you're more densely packed, you tend to see higher mortality rates. So lack of food, disease, competition. But to fluctuate just means to go up and down. So population size for all kinds of things, rabbits, coyotes, rats, deer, mice, bacteria, fluctuates. Algae in a lake or a pond, fish. You have a boom year and then something kills off a bunch of stuff. We talked in here about deer limits and how the limits, the bag limit changes every year based on the population data from the previous year. And those population numbers do fluctuate. There's a natural cycle. So this is a classic study, the snowshoe hare and lynx, that we'll talk about a little bit later. But what I want to do is think about this in terms of the rats. So if we think about population changes and fluctuations in terms of those rats, I'm going to draw a chart here. And let's say that this is our normal carrying capacity, whatever this population level is. And so, the rats have a good year and they have a bad year, and then they have a couple really average years. Every 48 years, what would you see happen at this carrying capacity level? This line would go whoop. Where does the crash put them? Does it put them all the way down to 0 rats? Does every rat die? No. The crash just returns them to carrying capacity. So if we looked at, the really long-term view, we would see something like that every 47 years. And that crash would return them back to carrying capacity. Could it drop them a little bit below carrying capacity? Yeah, it could. Carrying capacity isn't some absolute number. We can support 1,326 rats, period. It's an approximation. So very often we'll say, what's a reasonable estimate of carrying capacity? And it may not be a hard and fast final answer. So, you might very well see that population dip a little bit, and they have a good year, and and then we're back to those kind of fluctuations until we get to another spike. Populations fluctuate, and when they do, it is generally because of some kind of change in the environment. So in this case, it's due to the fruiting of the bamboo. It's due to a food source. You copied an illustration from your book about tick Who here has ever had a tick on them? Deer tick. I have a confession to make. I'm kind of a tick magnet. Ticks dig me. It's true. Actually, it is. Some people are more attractive to ticks than others. I happen to be one of those lucky people. Me and 10 other people can walk through a field. They all come out clean. I got 20 ticks. I don't know why. It's been that way my whole life. My best friend was the same way. And we were in a field botany class together, and we'd come back from a day in the field, and everybody else is like, I don't have any ticks. And we're both like... So, ticks. We didn't have a whole lot of deer ticks around here 20 years ago. We now have a pretty good deer tick population. What changed? Did deer numbers change? Did mouse numbers change? They're both part of the life cycle. I don't know the answer. This is not a question to which I have an answer. I don't know. It would be a fascinating point for research. What I know is that as a kid who spent about half my time out in the woods in Columbiana County, Ohio, I never had a deer tick on my body as a kid. And in the last few years, I get several deer ticks every summer. We used to see dog ticks, the big ones, the ones that are the size of a pencil eraser. Those little tiny deer ticks we did not see 20 years ago. Something in the environment changed. That's what causes fluctuations in populations. Who here has had both dog ticks and deer ticks on them? At the same time? Are you a tick magnet? Huh? Okay. Or you may have pulled them off your dog. Dogs commonly, you find big, nasty-looking ticks on the dog. But when a population fluctuates like that, something changes. The illustration in your book talked about a really good crop of acorns yielding a bigger food source for mice, which yields a bigger crop of mice, and that bigger crop of mice yields a bigger crop of deer ticks, and you end up with more Lyme disease cases in humans. changes in the environment cause changes elsewhere. Everything's connected. That's the big idea. Everything's connected. We're going to stop right there. I'm not giving you any homework or anything else to work on over the weekend. Go, enjoy it. It's supposed to be beautiful. But what I would ask that you do, carefully look over that viewing guide. I'm going to let you keep it if you feel like that's safe. If you want to get it in the box and out of your own hands, do that so you don't lose it if you're prone to losing things. But I want you to be, Tuesday when we come back, we're going to continue to talk about population fluctuations, and I want you to then get that viewing guide out because it may inform some of your answers. And I'll give you credit for having done it on Tuesday. Like I said, if you're afraid you're going to lose it, stick it in the box, pick it back out on Tuesday. But that's where we'll stop for today. I would suggest that you get Part C filled out on some of your vocab stuff.